Hi, my name is Shehryar Sardar, and this is my Physics 2211 Lab 3 Black Hole and Orbits. Table of contents. We will have introduction, models, black hole code, orbit code discussion, and conclusion. The purpose of this lab is to simulate the orbit of a star around a black hole to estimate its mass, and to simulate the orbit of a moon around a planet and a spaceship around the moon and a planet. Fundamental physics principles. First, Newton's second law. Force is equal to the mass times acceleration. Second, Newton's third law. For an applied force on an object, it will occur a force in equal and in the opposite direction. So F1 is equal to negative F2. Models. First, we have the universal gravitational force, which is equal to the gravitational constant times the mass of 1 times the mass of 2 over the radius between the two squared times negative r hat. Then we have the momentum, P equals mv, and F is equal to the change in momentum, and the update equations for velocity and position. Here is the results preview of the star orbiting the black hole on the left, and the spaceship and moon orbiting the planet on the right. Black hole code initial values. Most of the initial values are given to us, but we also need the mass of the star and the gravitational constant. We also need a way to calculate the average estimated black hole mass. So to do that, I added a total variable and a count variable, which we will use later to find the average. Black hole code loop. For the loop, our main purpose was to solve for the massive black hole. This can be found by rearranging the F-net on the star, which, due to the third law, is equal to the negative F-net on the black hole. To get the F-net on the star, we simply need the change in momentum of the star due to Newton's second law, and this can be found by multiplying the initial and final velocity by the mass and finding the difference. Orbit code, initial values. For the initial values, we need the mass of each object, the total time, and the delta t. Each delta t is around 60 seconds, aka 1 minute. For the ship's speed in x and y, these can be changed any values. However, if it's too low, then you may instantly crash into the moon, and if they're too big, the spaceship will be launched far, far into space. Orbit code, loop. For the first part of the loop, we need to find all the forces acting on a spaceship and the moon. This requires the gravitational forces of the planet and the moon and the spaceship. For the second part, we update the velocity and position for each based on the forces and the update equations. Here was a short clip of the orbit code running with my set x and y speed. As you can see, it has a very small orbit around the moon as it orbits the planet and lasts for a very long time before it eventually crashes into the planet. Discussion. Final results. For my estimated mass, I received around 1.51 times 10 to the 34 kilograms, and my x speed for the spaceship is 17,504, y 24,885. There's no similarities and differences, so there's only one model, and some sources of error for the mass could be insufficient data collection, and for the y, insufficient testing for specific values. Discussion questions. First off, what is the difference between net force and a change in momentum? Net force is what causes the change in momentum of an object. So they're not the exact same thing, but they're relatively similar. Second, what if for an imaginary system of a black hole, a star, a planet, and a moon, what forces exist and would they be more impactful than the others? For each object, there would be a gravitational force from every other object. The object with the biggest mass, such as a black hole or the star, would have a greater effect due to gravitational equation. In conclusion, we simulated the orbit of a star around a black hole and a spaceship around a moon and its planet. Thank you for watching and have a good day.